Adi, and welcome to this second session, okay, on the morning. This session we have 4 works. We are going mainly to deal with deep learning and neural networks. And the first presentation will be by Mikel Ferrero Jaurrieta about pseudo-grouping functions obtained by the distortion of aggregation functions and an application on text-based convolutional neural networks. So, Mikel, what do you want?
Okay. Thank you very much, Javier. Good morning, everybody. I am Mikel Ferrero Jaurrieta from the Public University of Navarre in Spain, and I'm going to present the work titled as Pseudo-grouping functions obtained by the distortion of aggregation functions, an application on text-based convolutional neural networks. This work has been done in collaboration with Ripaiva and Anderson Cruz from Brazil, and also with Zdenko Takac from Slovakia. Okay, as we know in this conference, information fusion is a very relevant task in several areas, such as economy, finance, software. Concretely, in artificial intelligence, as we know, this is very relevant in multi-criteria decision making, computer vision, and also in artificial neural network architectures, which is the field where we are going to apply this information fusion. As an examples of information fusion in this area can be, for example, the fusion of gates in recurrent neural networks. That there are the gates are, for example, the places where the information flow is controlled. Another example can be the pooling layers of convolutional neural network, where the information is reduced, attention mechanisms, etc. In this work, we are going to deal with time or sequential dependent. In this case, we are going to use aggregation functions according with this problem. The assumption of this problem is that the information we are taking into account is order dependent. However, in the literature, the mainly used aggregation functions are symmetric. What means this? This means that there is no relevance on the arguments that they are entering, that they are the input of the aggregation functions. Okay, so in this work, we are going to present and discuss about symmetry in information in sequential dependent information fusion, and concretely in text-based convolutional neural networks. From now on, text CNNs. For that, we are going to present a new method of constructing non-symmetric pseudo-grouping functions, and we are going to present some results where performance improvement are obtained comparing with classical symmetric operators. First of all, I'm going to present some preliminaries which are necessary for the subsequent developments of this work. The first one is the concept of the pseudo-automorphism, which is an unary function in the unit interval, which is continuous and increasing, is 0 when if and only if x is 0, is 1 if and only if x is 1. The second one is the classical fuzzy negation, which is a decreasing function with the following boundary conditions, and it's strong if it's involutive. We are in this work. We are going to use the core of this work are pseudo overlap and pseudo grouping functions, which are functions introduced in the following paper in 2022. These functions are generalizations of standard overlap and grouping functions, but in this case are were generalized by dropping out the symmetry property. Concretely, in pseudo-grouping function is an aggregation function, so it's increasing, is continuous, and it has the following boundary conditions. Is 0 if and only if all the elements, all input elements or arguments are 0, and is 1 if at least one input element is 1. Okay, now I'm going to present the new methods for constructing pseudo-grouping functions obtained by distortion of aggregation functions via pseudo-automorphisms. For that, I present the main definition, which is we take into account first n+1 pseudo-automorphism and an A aggregation function. We construct the B aggregation function in the following way. And in this way, we are going to call that this function is obtained by distortion. From this, we can obtain the following result for the case of pseudo-grouping functions. That is that a map taking into account the previous assumptions and the equation 1, the map B given in the following equation is a pseudo grouping if and only if also A is a pseudo grouping. From this result, we can obtain for example, the following example. We have taken as G function the identity and the following pseudo-automorphisms, which where we have a different exponent for each, different positive exponent for each one. In this case, we take into account the pseudo grouping. In this case, it's symmetric, but the constructed function it's not symmetric. Also note that if all the elements, all the exponents are the same, then this function is symmetric. Another result of this work is the following one, is that if we take n+1 strict fuzzy negations and we take also a pseudo overlap, we can construct the following pseudo grouping function obtained by the distortion of these negations. In this case, we also present an example that also in the application part we will use later. In this case, we take into account the following pseudo grouping function. We take the same strict negation for all of them, and we obtain the following pseudo grouping function. As I have said before, we are going to apply this in text TNNs. Text TNNs as the convolutional neural networks in general. There are neural networks that have the ability to extract spatial features from data. They are classically applied to images, but in this case, we are going to apply it in text. So in this case, text CNNs extract spatial features from text. The performance is almost the same, or is very similar as image one, but in this case we have one dimension less, so we are working in 1D, one dimension. Classically, text CNNs are divided in 4 layers. The embedding, convolution, overtime pooling, because the pooling is dependent on the time, on the sequence, and a linear layer. Now I'm going to explain briefly each layers. The first one is the embedding one. The embedding, the objective of the embedding is to encode the words into vectors to obtain a representation of each word as a vector, and therefore to obtain a matrix from a sentence. In this work, we are going to work with 2 kinds of embeddings. The first class of them is are the classical ones, the glove and fast text one, which are state of the art in this area. And then we are going to use also pre-trained transformer models, not as models, but we are going to use these models as embedding. We are going to obtain a representation to this for this data. So we are the embeddings transform each word into a vector, so we can obtain a matrix. From this, we want, or we have to obtain a representation, which are special features. So for the first two words, we obtain a feature. And this is repeated consecutively. For the second words, we obtain another feature. For the next words, we obtain another feature. Okay, but what occurs here is that, as occurs also in image-oriented convolutional neural networks, is that the features are redundant. So we have to fuse them in order to obtain a global one. As we have said before, the features represent a sequential dependent each other. As I have said also before, the most common functions used in the literature are arithmetic mean and maximum functions, which are symmetric. So the time dependence between these arguments, it is not taken into account. So in order to solve this problem, we have the following proposal. Our opinion and also our hypothesis is that this symmetry is not advisable in text CNS because the features are dependent. So we state that the symmetry plays an counterintuitive role because it may break the sequential or the temporal relation between the elements. For that, we are going to use pseudo-grouping functions. We are going to optimize them. The used functions are the maximum and the arithmetic mean, and also the following ones, which the two of them we have presented in the examples. And each exponent, positive exponent, we are going to learn with the gradient descent method inside the convolutional neural network. Okay, these functions are going to be applied in text classification and concretely sentiment analysis problem, and concretely in 3 datasets. The first one is related with question classification into 50 classes. The second one is a spam filtering problem where we have spam messages and ham or normal messages. And the third one is the IMDb classical dataset, which are positive, and we have to classify into positive and negative opinions of films. These problems are going to be evaluated into accuracy and F1 metrics. Regarding to the first dataset, we can see that the results the best results are obtained with the second pseudo-grouping function, and also the results have been compared with the Wilcoxon statistical test, and they are statistically significant. For each data set, we have done each run 5 times, and this is the arithmetic mean of the 5 runs. For the second data set, we have the following results. In this case, we have done with GLOB and with fast text embeddings. In this case, also we can see that the results with pseudo-grouping functions are better than the ones obtained with the classical functions. But in this case, only the F1 score related results are statistically significant, not the accuracy ones. Regarding to the third data set, and taking into account the classical embeddings, we can obtain also better numerical results for both classical embeddings, and also for all of them are statistically significant, taking into account Wilcoxon rank statistical test. And finally, taking into account transformer-based embeddings, we have the following results. Comparing with the previous one, we obtained better results, but the numerical comparison with the maximum of the arithmetic mean is lesser, and only there are statistically significant the one done with Viverta embedding, which is enhancement of BERT1. Okay, so as conclusions, we can say that optimized pseudo-grouping improves the symmetric operators, and they are statistically significant in almost the 80% of the cases. As conclusion also, it justifies the elimination of the symmetry property in artificial intelligence tasks where time or sequential information is going to be fused or is going to be processed. As a remark also that before this, it was noticed mainly in multi-criteria decision-making problems, and here we are presenting another problem. And finally, in the future, different tasks, but mainly time series based data we are going to use. This has been everything. Thank you very much. And if you have any question, I will try to answer.
Regarding that we intend to apply to bigger models and all that, have you had any real problem, any real application in mind for all this, or apart from the ones you have already tested? I mean, some kind of.
Yeah, we have tried to apply some modifications of this kind of neural networks in a project with the Justice Administration. In order to apply this in another specific tasks, which are not concretely classification on natural language processing, we have to change some restrictions, some requirements. But in the future, yes, we want to apply both in time series real problems and also in the project that we have with Justice Administration.
By Joshua Rodriguez Martinez, in collaboration with our friends from Slovakia. Okay, and the title is Fusion function combination to an extension of penalty-based functions for feature reduction in convolutional neural networks. Okay, whatever you want, Joshua.
Okay. Well, thank you, everybody. My name is Joshua Rodriguez, as Javi just said, and I'm going to present our work, which has been done in collaboration with Lubomira Franska and Stenko Takacs from the Technical University of Bratislava, as well as Francisco Herrera from the University of Granada in Spain, and Humberto Agustinte, which is my PhD supervisor. Okay, so to quickly set up the context of the problem, okay, similarly to what Mikel just explained about convolutional neural networks, my PhD thesis also focuses on the modification of this kind of architectures, okay, of machine learning, and in, well, specifically in the feature fusion processes that occur inside these neural networks. To sum it up very quickly, okay, convolutional neural networks extract, in the case of image and not text, extract visual features, okay, from the input data that we provide through the convolution of different filters, okay, of different convolution filters, which the model can automatically optimize through gradient descent and such. This process of convolution, okay, generates for each of the convolution filters that the model learns, generates a different representation, as you can see here, of feature matrices of feature images, which represent the presence or absence of such given features over all parts of the input image. This is very interesting because, of course, this gives us lots of information that then a classifier or a segmentation algorithm could use for performing their processes. But the problem, one problem, is that dimensionality keeps increasing throughout all the process, okay? Because we start from, for example, in RGB color imaging, three-dimensional image, and we can learn hundreds of such feature images. a classical solution to this problem, okay, in order to compress the information that we start, that convolutional layer extracts, is, are pooling layers, okay? That similarly to what Mikel explained. In this case, they take disjoint windows of the feature maps, of the feature images that have been extracted, and they summarize each of those feature of those windows into a single representative, okay? Usually aggregating their their values through the maximum or the arithmetic mean. Of course, in some instances, this could be a problem, taking just into account one of those reductions, because we could be losing some important features, okay, depending on the fusion that we are working with. So that is what led us in a previous work to present a new strategy which applies more than those functions, also some other functions from fusion function theory to the pooling process, and then combine the all the reductions through a convex combination of those functions. Here, the coefficients of the convex combination were optimized in the same way as the rest of parameters of the model in a supervised way, okay, through gradient descent. But in this work, we want to go a step further and take into account some results, some functions from the theoretical world. Okay, specifically, we will be focusing on penalty-based functions, which allow us to weigh the importance of how good each of those reductions is according to a given distance. Okay. So just a quick summary, okay? Well, we'll know what a fusion function is, okay? Just an arbitrary function that takes n inputs from 0, 1 and gives us a single representative. And of course, if we have the monotonicity and boundary conditions, we end up with the definition of aggregation functions. The arithmetic mean and the maximum that pooling layers usually use, of course, are examples of such aggregation functions. But there are many more in the literature that we would like to exploit, and an example of those functions are fuzzy integrals, okay? Which are very interesting from the empirical point of view because they allow us to weight the coalition among different subsets of the data that we want to aggregate, to fuse through the notion of a fuzzy measure. Okay, so of course, well, in our experiments, we will be using the Schocket and Sugeno integral, okay? But I will just skip ahead, okay, because I think that we have seen them already throughout this Congress. But, okay, a problem or, well, a restriction of aggregation functions, of course, is that monotonicity can be a quite strict condition for some functions that are interesting from the experimental point of view. Okay, for example, the mode, which is not monotone. So that's why in the past the concept of pre-aggregation function was introduced. Okay, which replaces the notion of monotonicity by monotonicity or increasingness on a direction given by a vector A. Okay. So we can say that a pre-aggregation function is a fusion function which follows boundary conditions and which is increasing, are increasing in a given direction. And now we can already go to the main focus of the presentation, okay, which are penalty functions. Penalty functions are functions which receive n+1 inputs, okay, a vector of n values f, x, and a single value y, and they return 0 whenever all the values on x are equal to y, okay? And it's quasi-convex in y for any x. So this means that the closer the vector x is, well, all elements of x are to the value y, smaller, okay, the output of the penalty function will be. Why is this useful for us? Well, because we can use this concept of penalty function in order to define penalty-based functions, okay, which in some previous work, Belyakov and others have studied a lot, okay? But we give here kind of a redefinition, which we call PA functions in this sense, okay? So if we have a penalty function, okay, and a set of fusion functions, of K fusion functions, then we can find the penalty, well, the PA function as the arithmetic mean of those functions which minimize the penalty, okay, from out of the set we have. some interesting properties here are that depending on the fusion functions that we select, some properties are inherited by the resulting PA function that we construct, okay? So this happens, for example, for boundary conditions. Also, if all fusion functions are idempotent, then our resulting PA function will be 2. And the same happens for if they are averaging, okay? But this does not follow for monotonicity, okay? So therefore, even if we select k aggregation functions, the final PA function will not be an aggregation in general. However, well, if we take the concept of shift invariancy of shift invariant function and we extend it to the concept of penalty functions in such way, okay, we can say that whenever the fusion functions that we are working with are shift invariant, then the resulting PA function will be both shift invariant and increasing in the direction given by the vector where all elements are 1. So therefore, if the fusion functions that we select are shift invariant and also follow boundary conditions, then the resulting PA function at least will be a pre-aggregation function, okay? Even if it is not an aggregation function in general. Okay, well, so now going back to our problem, okay? We have said that we want to use different reductions on the pooling process, okay, of our convolutional neural network. And when we previously combined all of them through a convex combination, we will now use a PA function in order to select the best of those reductions according to the penalty that we have selected, okay, to that distance. So this is something that we can do and we have done and works quite all right, okay? But we can go even a step further, okay? If we define a generalization of such PA functions in the form of a WB PA function. What is a WB PA function? Well, similarly to PA functions, we have once again a penalty function and a bunch of fusion functions, and we need to define a weight vector, okay, which follows that the weight assigned for a specific element of the set of functions we are working with will be bigger the smaller the penalty is for that specific reduction. Okay, so in that sense, well, then we will combine all those the output of all those reductions through a convex combination, but the coefficients of those convex combination will show us in some way how good the reduction was according to the penalty, how much it penalized, it reduced the specific penalty we have set. Of course, a PA function in general is a specific case of WB PA function when we construct the vector WB such as this, so that we have 1 divided by the number of minimizers of the set for those elements which are minimizers and 0 for the rest, okay? And we have, once again, the same situation as in PA functions, where boundary conditions, idempotency, and such follow from the properties of the fusion function selected, but this does not happen for monotonicity. Although, once again, if they follow boundary conditions and shift invariant, then the resulting WBPA function is a pre-aggregation function, okay? So now, of course, the important part is seeing a way in which to construct such WB vector, okay, that follows the properties that we have selected. A simple approach would be to perform this construction in 2 steps, okay? Firstly, we can define, well, we can select a decreasing G function, okay, defined from 0 to infinity. And after applying all our reductions and weighting them, well, and applying to them the penalty function that we have selected, then to the output of the penalty, we can apply this G function, okay? So in this sense, the bigger the penalty will be, then the smaller the contribution that it will be have later on. After applying this, we will have kind of a non-normalized weight vector, okay? That, of course, we can simply normalize using a normalization function S. And then through such a construction, we can end up with the with the weight vector that we require for our convex combination. In our experimental setup, we have tried just a couple of those G and S functions, but of course, much more will be tested. Okay. And again, if we go back to the idea of conf pool layers, now we also would like to test the idea of applying several K reductions to each of our disjoint windows, analyzing them through the lens of our penalty functions in order to see which one minimize it more and which one minimize it less, and apply our WPA function to weight more those which minimize more the penalty. Okay. In order to see if this performs correctly, okay, in practice, we have set up a simple experiment. We have just tested the Zipf-Arten dataset, okay, which is a standard dataset which works with small color images of the real world. And we have modified a simple ResNet model, which is quite standard on computer vision, okay? We have replaced the feature reduction process of ResNet by our proposed pooling layers. Okay, well, initially we have tested simply different fusion functions, individual ones, okay? Not just the arithmetic mean and the maximum, but also the Schocket and the sui generis integral. And we can already see that the Schocket integral leads us to good results. But if we apply both our original idea of conf pool layers and the idea of PA function, we can see that how we can outperform individual aggregations, well, reductions. However, here see that conf pool layers which simply learn the coefficient of each element of the combination outperform PA functions which simply select one of the given reductions. However, when we extend this to when we apply WPA functions in order to learn those, well, to get those coefficients, then we have some instances in which we outperform even the supervisedly optimized method of conf pool layers. Okay. This is a lot of numbers, okay, but we should have a more in-depth study in the future with more concrete examples of functions that perform correctly. So as conclusion, well, we have seen that the concept of penalty is useful when we want to combine different reductions of several reduction processes, and that the idea of WPA function can be beneficial or can even outperform the idea of PA functions on practical settings. Okay. And of course, we would like in the future to have a more in-depth study and maybe provide some alternative construction methods for such functions. And we would like to keep on replacing some fusion processes on different deep learning or machine learning models. So that's everything. Thank you for your attention. And if anyone has any doubt, do not hesitate to ask. Thank you.
Yes.
How did you choose fuzzy measures for short-term integrality?
Yeah, in this case, we haven't optimized the fuzzy measure. Okay, we just set up the power measure. I think that exponent was 2, because we did some quick experimenting and we did not go too much in depth to the optimization of the fuzzy measure. So we think that we could even outperform this if we use some strategy, like for example, as Gracelis presented yesterday, or other optimization procedures. But here it was simply static. No, there was no learning applied to the fuzzy measure.
And you want to create function of any variable aggregation function. Isn't there some problem? Because usually it's composed from, say, binary things, by summation and something like this. So how you have chosen your penalty functions, which are in general functions of n+1 variable?
Yes, well, in this case, in the way in which we have defined here, okay, yeah, well, really, the penalty function does compute the difference between each element of X with the element of Y, and then an aggregation of such differences is.
Sets combined.
Yeah.
And this, there is a one after that one, that, which there was a discussion about that. And then we have a new definition that, surpass all the drawbacks of vision including. And then, I suggest you
Yeah.
the definition, and also we have a study on payment-based functions defined by pre-aggregation functions. Based
Okay.
on this new definition.
Yeah.
Based on this.
Yeah. We know that there was quite a lot of literature of pre-aggregation function. We just started from some point, but yeah.
Why you use the definition? Suggestion.
Yeah. We should.
Because it's a large discussion.
Yes, I know.
But then after that, I think, I don't remember in which year we proposed, in 2017, I think. Was a new definition, and after that, in 2018, also a study on pre-aggregation functions and properties based on this new definition.
Mhm.
That solve all the drawbacks of the definition, including.
Okay. Yeah. No, I think that we should check that out, and maybe even with that definition, the extension to double PA functions could be also performed, because we in some sense need the PA function in order to weight, well, the penalty function to weight how each fusion function behaves, no, with relation to this penalty. And I think that we could take that new definition and replace it here and see if it breaks anything or not. Yeah. I'm pretty sure that it is possible. Yeah.
There at least some comments on that.
Yeah.
And
Thank you.
some that with the new,
Mm.
they are for it.
Okay. Thank you.
More questions or remarks? No, and the speaker, thank you very much. The next speaker will be David Ansinger. I hope I have all. Okay, and the title will be efficient use of large language models for analysis of text properties.
Thank you for the introduction. Today, I am going to talk about my joint work with Yanura. And in this presentation, I would like to show you how you can use large language models for efficient processing large amount of data. So I would like to start with the problem statement. We would like monitor phenomena in large language corpus, which means, for example, we would like monitoring discussion on the social media. So we have very big data sets with the comments and with the timestamps. And we would like prepare something like this. We have frequency and the time. Here is, for example, months, and we would like compute how people talk about some events at the social media. For example, they can command the weather or political election, and so on. So the naive approach is classify each or every command in our dataset, but it is very complicated when you have very big data. So it is also very expensive and very slow. So here you can see example when you try process about 200 commands with the GPT API. I mean OpenAI API. So in the table you can see the tokens, the price. It is cheap, but only for 200 commands, and the time it is about over 300 seconds, but the accuracy is very bad for GPT 3.5, and it is better for GPT 4. So we have datasets with contains over 200 millions of the commands, and we expected the prices over 20,000 USD, and the expected time is over 3,000 days. So it is not possible. So the motivation is analyze our data, and in this presentation, I would like to show you the example with the discussion about the political election in the United States and the discussion about the weather. So here is the description of our data sets. We have the data from years 2019 and 2022, which is divided into individual months. So there is probably about 50 millions of sentences in 1 year. And here you can see the total amount of the sentences. So now I would like to show you the basic idea of our pipeline. You can see on the top is the human work, and on the bottom is the cheapest solution for the filtering of the data. And it is also very expensive to use human work for the labeling all of the data, but it is also very slow. So for this, we would like to use the most possible cheapest solution to filter necessary sentences, and we would like process this for amount of the data. And then we would like go to the top for the smaller model, which is very fast. And in this position, we can compute the not probability, it is confidence. It is confidence of the prediction, and we can decide if we need to go to the top position or this position. So we can save in this way very big time. So the first step is sentence filtering. So we have the data sets, and we would like compute the embeddings for our words in the data sets. So you probably know when you use fasta, which is the extension of the word2vec, we have something like this, and we can compute the embeddings. So the words, it is similar. The distance is very small, and the words which is different, the distance is very big when we use cosine distance as the measure. So we compute our embeddings for words in the data sets and we save this embedding into the vector database. And then user can ask for the some words which can be used for the question. So we can select all synonyms in the data sets and we can use these synonyms for filtering all sentences from the data sets. So this is the first step, which is very efficient. Now you can see the examples of the input words. For example, for the discussion of the weather views these words, and for the discussion about the political election views these words as the input here. So now we would like sample some training data, and we need to prepare the data sets for the training. We would like prepare embeddings, but not from the words, but from the sentences. And we would like in the same way select sentences which is very similar in the thematic way. So for example, we can create the clusters and we select the cluster and we assign the label for this cluster. So it is very efficient way, and we can create the data sets very fast. Also we can use the manual labeling or the OpenAI API. So now I would like to show you the prompts for the experiments with the weather discussion. We would like ask the model, does the text imply hot weather, cold weather, or it is not about the weather? And there is the option. And here we would like put the sentence from the data set. This is the second prompt for the experiment with the political action. We would like ask if this text is about the political election, and the option is only yes or no. So now we would like perform the training. We would like use Plan-T5 model XXL, and then we prepare the model distillation for the small model, which is very efficient. So now I would like to show you the pipeline for the inference. We would like also use the previous process for the sentence filtration, and then we would like use the small model to classify the sentences. And then we check the confidence, and if the confidence is sufficient, we can save the output label, or we can delegate the classification to the better model. So here you can see the example for the discussion about the weather. The red color is discussion about the hot weather, and the cold and the blue is about the cold. So you can see the February people talk about the cold weather, and in the June or July people talk about the hot weather. And this is the second experiment, and you can see in the November people talk about the political election in the USA. So now I would like to show you the average prediction speed. When you classify one sentence by OpenAPI, it is about 1 second on 20 seconds. Sometimes it is very complicated because they don't support some type of request and so on. In the Plan-T5 XXL, it is better, and the best performance is with the set-fit model. So now you can see the sentence filtration for the discussion about the weather. Here you can see the number of sentences, and here you can see the number of the time for the years. It is also the same table for the different experiment. And now I will show you the performance. When we use only fluenty5, it is about 660 hours. But when we use the pipeline, it is more faster. It is about 4 hours or 12 hours. So for the future work, I would like to compare this pipeline with my other approaches, and I would like prepare some design patterns or design for machine learning systems. This is all. Thank you for the attention.
For having this result. Any question, comment? If not, just one question.
Mhm.
Have you had any estimation about the accuracy? Up to what extent you have actually correctly classified all the comments that were in the.
Well, we use something for this in the first table, and we perform only 200 commands, and we prepare the manual labeling, and then we can compare because the manual labeling is ground true for us, and then we perform the classification by ChatGPT, and it is not possible to compute all of the data.
I was wondering, because especially if you are thinking about the discussion on politics, maybe politics, some people are making comments which do not seem to be politics. Okay, maybe you are using a language or something like that. So it's in that sense that people asking you if you are sure that those comments are also actually catched by your system or are not catched.
Oh, okay, this is a very interesting question. I think the problem is create the prompt for the fluenty5. When you create the good prompt, it is possible to catch all the edge case.
Okay. Any more comments, more questions? If not, then thank you, speaker. Thank you very much. And we go for the last talk of this session, okay, which is going to be given by Iñaki Pérez del Notario. Okay. Pamplona, and the title is Early Warning of River Overflow Flooding Using Artificial Intelligence. So whenever you want.
Hello, good morning. My name is Iñaki Pérez del Notario, and I'm doing a PhD about predicting floods and reduce the risk of disaster. This work is done with Humberto Bustince and Pello Oria. And this work is also done on the private company Tesignor and the Public University of Navarra, with the collaboration of the Meteorological Estatal Agency, IMET, and with funding from the government of Navarra. First, I'm going to introduce the problem of floods. Floods is the most common natural disaster in the world that worldwide causes a huge amount of damage when this event happens. This all leading to great economic costs and people losing their homes or properties, and with possible casualties on the citizens. The four most common causes are river overflows. We have some episodes on Pamplona, a city of Navarre in Spain, and severe rainfalls that can cause a flood by the water getting stuck under the surface.
Other less common possibilities are tsunamis after an earthquake, or also dam failures, like the ones you may have already seen on cartoons. Our objective is to anticipate these events so we can advise the authorities and the citizens to evacuate and reduce the damage. There are two possible techniques that are used to dealing with river flow prediction. One is by using physical models that use physical equations to estimate how the river is going to behave on the following hours. Another approximation is with using AI. Instead of using physical laws, instead of knowing that, we learn what are the patterns that lead to water increases and make a prediction. The principal advantage of AI compared to physical models is that physical models need several hours to compute. And when you get the results, that is already outdated. With AI, you can make a prediction with only a few seconds, and the prediction is made with the most recent data. The available data that we use for doing this research consists of meteorological values from the statal agency and hydrological variables from hydrologic confederations. This consists on river flow values, rain gauges on different points of the river, and temperature values. On the meteorological side, we have precipitation predictions for the following hours, a reflectivity radar, which is a technology that estimates the amount of rain that is falling on a certain place, and the soil moisture, which is the humidity of the terrain. If the terrain is humid, it's more likely for the water to get stuck. Now, I'm going to talk about the models that work better for us. On the first scan, we have LSTM neural networks, which are recurrent models that learn time-related patterns. And on the other side, we used an adaptive neurofaci inference system, which in this problem, this model learns with Faci logic, distinguish between different states of the data. For example, if the river is behaving normally, or if we have an anomaly, what kind of anomaly, how it's going to behave with this anomaly, and that kind of thing. This AMFIS also implements a generalization of Takagi-Sugeno-Kan, which is the one that presented Xavier Gonzalez this Monday. This briefly explained, this generalization replaces the minimum and product abbreviations on the antecedent layer of the rules and on the antecedent part, and allow us to use more flexible ones like OWASP, geometric means, integrals, etc. Also, this initialization includes a tau parameter, which is a parameter that on the original Takagi-Sugeno paper, it refers to the degree of truth of a rule. In our case, we made this parameter being optimizable by the grading, taking values between 0 and 1. So then it can deactivate a rule when it's not needed. Another modification is that we replace the normalization layer that is before we get the firing strength of every rule. One of the problems of the AFIS model is when you have a high number of rules, when you get an input, usually a lot of rules have values higher than 0, but very low. But when you have a lot of rules with very low activation rate that are not interesting, that is noise. And that affects the final prediction, and we don't want that. This method is developed by these people over here, consists on has a first step of scaling the activation of the rules, then applies a layer normalization to make the mean 0 and the standard deviation 1, and then a ReLU layer which filters the rules with very low activation rate, so we only have left the ones that are really necessary and important. For the results, for training the model, we used an mean average error, but as this is an unbalanced problem because water risings are not that common, are relevant, we apply a penalization parameter, which in cases of water risings, apply a penalization to increase the error of predicting bad this event. This way, we don't have to make data oversampling or undersampling, and we can train with all the data, and we avoid cases of predicting a rising when it's not going to happen. Also, if this twinges, if the real values are, if the predicted values are above or below the prediction, because we want to overestimate a little bit. We prefer to overestimate than underestimate. These are some performance comparisons. As I said before, the models that best work for this application are ANFIS and LSTM with similar performance in general. Yes. In training and validation are different, but in test are the same. Other models that we try are artificial neural networks, which doesn't have the capability of recognizing different states of the river. And this is a problem, and that is the cause that they have not that good performance. Another model is an XGBoost regressor, which also learns different stems of the data, but they are not as complex as neural networks, so they doesn't get as good performance. This is the case of an episode of flooding that happened on 2019 on the city of Pamplona. In this case, we compared the two models, and the first one gives better anticipation at the start of the rising, but then it gets here a little bit short. LSTM doesn't get that good anticipation, but is more consistent on the rising, which made both models good when working together. This is another event, which is the more severe episode we have in Pamplona. And in this comparison, both models, I think they behave the same with small differences. They both reach the peak values, which are values that this level of value doesn't exist on the training and validation data. So you can see that this model has some sort of future proof. Now I'm going to talk about problems of the real world. We have this model on a system working on real time, receiving data for the data suppliers, but we have had some issues. One of them, if one of the connections with the suppliers fails, we cannot make prediction. We don't have every data available. Another problem is when we receive data, but this data comes with wrong values, maybe for whatever reason. So, on the first case, when the system stops working and we, after a certain amount of hours, we regain connection, then LSTM, as it depends on previous states, is not able to give reliable predictions. With that, you can see that the model predicts whatever things you want. This is not a problem with the ANFIS because it only needs a current state. So the moment we have data, we make a prediction and this prediction is reliable. Then we have other cases when we receive wrong input values. Where in the case of the AMFIS, as it only has the current data, this is very affected by noisy values. LSTM, you can receive a noisy value, but the neural network is capable of noticing this is a noisy value and give you a more reliable prediction, which is an interesting property. Now, to end, as a conclusion, we have developed an early warning system that alerts from floods that happened that will likely going to happen on the next following 8 hours. And both AMFIS and LSTM has some advantages and disadvantages that when working together, they make a solid system, more solid. To end the presentation, I want to mention that we are currently working on predicting radars, on predicting floods caused by heavy precipitations, by heavy rain. This is done by a technology that I explained earlier, which is the radar technology that estimates the amount of rain is raining on a certain place. And we want, with the previous images, predict how a storm is going to move. If this heavy storm is going to go to a municipality and cause a possible disaster. We are doing this by using generative adversarial neural networks, which are the ones that likely, well, on the state on the art gets better results, and a generator that combines convolutional neural networks and recurrent neural networks. And this is the end of my presentation. I hope you like it.
Very much interesting presentation. Some comments, some remarks, question. Some questions, I'm very interested in this. So first of all, the model that you have created would be valid for any kind of river. I mean, I mean, with the data you are using, or you will probably need a different type of data. Or
Depends on the data. For one river, it can work better for another. We have with some rivers, for example, the Aragon River, that with a simple model, we can get up to 12 hours. It's more predictable model. There are other rivers that are less predictable, and maybe they will require or more data or more advanced techniques, which we will know when we are further developing, expanding the tool for different rivers.
are you expecting to improve this 8 hours time? It's very hard.
We're going to try to improve. I don't know why or how, but we will try. For the tables, you see that it matches the prediction. It also depends on the data. We can have here a scale here, which is caused by certain wrong values on the data. But maybe if we increase the range, we could see if we can improve this number.
Thank you. Some more questions, comments, remarks? No, we thank again the speaker. Enjoy the session, enjoy the meal, bon appetit, and enjoy the drink this afternoon. Okay.